All right, open up your book to section 10-3. We're on page 508 in your book. The title of this section is Parametric Equations for Conic Sections. And the objective here is given parametric equations for a conic section. Identify which conic section the graph will be. We're going to plot the graph and confirm your identification by transforming the parametric equation into a Cartesian equation. If you recall in the previous section here, we were dealing with Cartesian equations. We actually saw a couple of different forms there, that polynomial form as well as either that center radius or vertex form depending on the conic. And we kind of worked with those Cartesian equations. And now we're going to jump into parametric equations. All right, before we take a look at the equations there for these conics in parametric form, you may recall back in chapter 1 when we were dealing with inverses, we were using parametrics to help us sketch inverse functions. And if you recall, when you write the equation of a parametric, you end up with an x equation and a y equation. You have a new independent variable that gets introduced. The x is introduced as the independent, or sorry, the t is introduced as the independent variable, and then x and y are both written as equations in terms of t. And in fact, we were kind of introduced to this idea in chapter 7. We were actually sketching some ellipses back in chapter 7 in parametrics. So you saw a little bit of this already. All right, let's take a look at the circle to start off with. Again, with a parametric equation, remember you got an x and a y here. So I've got x is equal to h plus r cosine of t, and y is equal to k plus r sine of t. So that is the parametric equation for a circle. The h and the k represent the center, and the radius is r in that equation. So x equals h plus r cosine of t, and y equals k plus r sine of t. Notice that the cosine is with the x, and the sine is with the y. If you think of the definition of sine and cosine in terms of u, v, and r, cosine is u over r. U represents the horizontal and x value. That might help you remember that. Sine is v over r. Sine is v, which is the vertical, the y component there. And so in this equation, you see that sine is associated with the y value. All right, but there's our equation of a circle in parametric form. All right, let's take a look at the ellipse. The ellipse, we shouldn't be surprised, is going to look very similar to the circle. In fact, we saw this when we were looking at the Cartesian form, when it was that center radius form. The equation is basically the same here, except instead of using r, we're using d sub x and d sub y to represent our x dilation and our y dilation. So you have x is equal to h plus d sub x times cosine of t, and y is k plus d sub y times sine of t. And again, your center is at hk, your x dilation is the d sub x, and your y dilation is the d sub y. That right there is our equation of an ellipse in parametric form. All right, for the hyperbola it does depend on which direction this opens up in. So for the hyperbola, we've got two equations here. The first one here is if it opens up in the x direction, so it opens up to the left and the right. You end up with x is equal to h plus d sub x times the secant of t, and y equals k plus d sub y times the tangent of t. So we're using secant and tangent as opposed to sine and cosine to get the hyperbola. So that's if it opens up in the x direction. If it opens up in the y direction, notice the only thing that changes there is that we change the change the secant and tangent. Switch those around. So we have x is equal to h plus d sub x times the tangent of t, and y is equal to k plus d sub y times the secant of t. Notice that secant goes with the direction that it opens up in. If it opens up in the x direction, secant is with x. If it opens up in the y direction, secant is with y. Remember it that way. It'll probably help you remember the right way. All right, over on the right then, it tells you all the the information here about this. This is, by the way, the same thing we talked about with Cartesian. We're just seeing over on the left a different way to write this. So the center is still at hk in both equations there. You've got an x dilation and a y dilation. You can find the slope of your asymptotes there by calculating the y dilation divided by the x dilation. That's plus or minus that. Again, one's positive because one's an increasing asymptote. The other one's negative because it's decreasing. And again, you can determine the distance from the center. Let me scroll down here. From the center to the vertex by looking at dx or dy, depending on which way this opens up. So if this opens up in the x direction, like you see in equation 1, then dx will tell you the distance from the center to the vertex. On the other hand, if it opens up in the y direction, then dy tells you the distance from the center to the vertex. Again, that's the same thing we talked about with our Cartesian equations. All right, so we have one last one here to talk about, and that is our parabola. And again, just like we saw with our Cartesian form here, it does make a difference which way this opens up. So if you've got yourself a parabola that opens up in the x direction, then here's the equation that we'll use. Our parametric equation is x is equal to h plus a times t minus k squared, and y is equal to t. Notice, by the way, if all we're doing is taking the y out of that equation we had in Cartesian form and replacing it with t, and then we're saying y equals t in the second equation there. It's literally a substitution is what we've got to get the other form. On the other hand, if it opens up in the y direction, then we have x is equal to t, and our equation becomes y is equal to k plus a times t minus h squared. And again, if you look at that equation there, and you literally take the t in the second equation and replace it with x, because x equals t, you'd end up with a Cartesian form. It is literally a replacement or a substitution of that variable is all we're doing to get to the Cartesian form from this parametric form. And again, over on the right there, we've got the details on this one. This one's called the vertex form there because of the fact that it doesn't have a center. So the vertex is at hk. You've got a dilation factor of a, and again, we're just calling it a dilation factor because instead of horizontal or vertical or x or y, because it depends on which way this opens up as to what dilation factor it's going to be. So if it opens up in the x direction there, then it's an x dilation. If it's in the y direction, it's a y dilation. So it depends on which way it opens up. Anyways, a is the dilation factor. And then you have an axis of symmetry that goes right through the middle of that thing and crosses the vertex, of course. It's perpendicular to your graph at the vertex. And so that's the line y equals k. If that's equation 1, if it's opening up in the x direction, then it's a horizontal line that we need. So y equals k is that horizontal line. And on the other hand, if it's equation 2, where your parabola opens in the y direction, then x equals h. H is our vertical line that we need for the axis of symmetry. So that right there is the two equations that we have for a parabola in parametric form. All right, let's take a look at a couple of examples here. Example number 1 on page 510. This says write the parametric equations for the parabola in figure 10-3 and confirm your answer by plotting it in parametric equation, by plotting the parametric equation on the grapher. Okay, so let's find the equation of this thing, and then let's see if we can actually graph that on our calculator. All right, so we've got the sketch here. I guess they already told us this, but I'm still going to write down what exactly the conic is that we're looking at, and then we'll fill in the details about it. So again, they did tell us it was a parabola, but that would be the first thing we need to figure out if they didn't tell us that. Got ourselves a parabola. The second thing to note, since it's a parabola, is which direction this is opening up in, because remember the parabola and the hyperbola have two equations, and it depends on which way this opens up. So this opens in the x direction. And If you want to be even more specific and say that it opens up to the left, you could, but that doesn't determine the equation that we're going to write down. It does help you understand what value of a we should be getting, but that gets us enough information to get the equation. So our equation is going to be x is equal to h plus a times t minus k, and that's squared. And then we have y is equal to t. All right, again, go back and look at the parametric equations for the parabola. And it opens up in the x direction. These are the two equations there that we have for that parabola. All right, the first thing that we should be able to find on this is the vertex. So let's do that. I think that's pretty obvious. Right here is our vertex. And that looks like that's over here at 5, and up, looks like it's up at 2 here is our vertex. So we can say that our vertex is at 5, 2. Which again is that's our h and our k. So we have our h and our k. The only thing left that we've got to find is that value of a. But actually we've got a little bit of work to do in order to come up with that. In fact, I guess we could write this out here in its... Let me separate these just so I can see those a little bit easier. Let's rewrite this with h and k in here. So x is equal to 5 plus a times t minus 2 squared, and then y is equal to t. That's what we have so far. We found our h and our k. They gave us another point here, not only the vertex, but they gave us an x-intercept. And so that x-intercept looks like that's at 3, 0. So that's an x and a y value. So I know what x is equal to, and I know what y is equal to, so I can use that to help me come up with my value for a. We had to do something similar to this when you're trying to come up with a in Cartesian form. So I've got that, maybe I'll put that in the same color. I had that in purple here. So I've got x is equal to, actually let me do that over on the side here. Got x is equal to 3, and we've got y is equal to 0. And actually, since y is equal to t, we also know what t is equal to. So we also know that t must be 0, because y equals t. All right, so with that, I should be able to plug that into the first equation and find out what a equals. So from the first equation there, it's x, or that's 3 for us, is equal to 5 plus a times, the t value is 0, minus 2 squared. So I've just plugged in my x and my t value, and my h and my k, and I can now solve that for a. So what do we end up with? Subtract the 5, and we'll end up with a negative 2 over here on the left. Negative 2 squared is 4, so that's 4a over there on the right. Divide by 2 would give us a negative 1/2 is our value for a. All right, so with that, I should be able to write my equation now. We've got x is equal to 5 minus 1/2 of t minus 2, and that's squared, and y is equal to t. There's our equation. That's a very similar technique to what we had to do when we were working in Cartesian form. We did have this one little extra piece here, or extra step. We had to also find what t equals. But since y is equal to t, that's pretty easy to do. All right, so now let's graph that and see if we, in fact, end up with the graph that they gave us. We end up with the same thing. Grab your calculator. All right, so let's go to our mode first, and let's switch over to the right mode. So I want to get our calculator into parametric mode is the first thing. And I guess you can sketch this, whoops, did not get that into parametric mode. There we go. You can sketch that it won't matter whether you're in degree or radian mode for this one because it's a parabola, but when you look at the other three conics, those involve the trig function, so it will make a difference whether you're in radians or degrees. But in this case, it won't matter, so I'm going to leave it in degree mode here. Let's go to our y equals menu. Oops, let me get rid of those equations there. I don't need those. And let's put in the two equations that we just came up with here. So we had x is equal to, it was 5 minus the 1/2, or 5 minus, I'm going to write that as 0.5, I think, to put that in there, times t minus 2. and that's squared. That's our x equation, and our y is pretty simple. That's just equal to t. So there's our equation that we came up with. Now when you go to your window, remember you got t range to set here. Now since I've got the equation that y equals t, I'm going to pick my t values to be the same as my y min and my y max. So I'm going to just go from -10 to 10. And I do want to pick a t step small enough to get an accurate sketch of this thing, so I'll make it 0.1. And the rest I think we can sketch in the standard window here. So let's go ahead and graph that. And yeah, right there we go. That looks like a pretty good sketch of our parabola. And I think if we compare that to the original graph they gave us, that is a pretty decent sketch of that graph. All right, take a look at example 2. Example 2 asks us to do the same thing, but it's a different conic here. Write a parametric equation for the hyperbola in figure 10.3b. Confirm your answer by plotting the parametric equation on your graph. Okay, so we're going to go through the same steps here, but now we've got ourselves a hyperbola that we're working with. They told us that in the problem, but obviously that's, again, this place to start. Make sure you recognize the conic that you're dealing with. I'm going to go ahead and write that down, hyperbola. And remember, with the hyperbola and the parabola, those have two different equations here. So I should write down which direction this opens up in. It's definitely opening up in the x direction. It opens up over to the right here and over to the left here. So this opens in the x direction. Opens up in the x direction. All right, so with that, that's enough information for me to write down my general equation here. So let's do that. Remember that the hyperbola equation is the one that involves secant and tangent, so make sure you got the right one here. Secant is the one that's associated with the direction that it opens up in. So secant is going to be with our x here then. So we've got h plus d sub x times the secant of t. And we've got y is equal to k plus d sub y times the tangent of t. Again, go back and refresh your memory on those formulas there to make sure you understand that there's two different formulas. And the question is really where does secant and tangent go? Since it opens in the x direction, that tells me that it's secant there. Maybe I should underline that for us there. It's going in the x direction, which is what's telling me that x has the secant. All right, so again, we've got four things to find out here. This is the same story that we've had with Cartesian form when we were finding the equation of the hyperbola. Was we had four things to find, the same four things. So let's go through and find those four things. Let's start out with the center of this thing. That's the easiest thing, I think, to find there. Looks like that's at -5, and this looks like that's at 4. So the center is at -5, 4. All right, and well, that's the HK, so now I just need my X dilation and my Y dilation. And again, to find your X dilation and your Y dilation, you'll do the same thing we did with Cartesian form. And that is we have to measure this distance from the center to the vertex. So that distance right there is what we've got to measure. That clearly is 2 units. So that's the change in X there. That's my X dilation is what that is. So I'm going to write that as dx. Again, if this was opening in the y direction, then when I measure that center to that vertex, it would be a vertical direction, so that would be my dy. And then from that vertex, if you measure up to your asymptote there, that has to represent the slope between those two of that asymptote there. So this must be the change in y, or the rise of this thing, which looks like that's 1, 2, 3 units there. So this is 3. That is my change in y, so that's my dy, d sub y. All right, there we go. We've got everything we need to write an equation now. All right, so HK is the center of this. That's at -5, 2. I kind of like filling this in kind of simultaneously as I do this here. You can do it just X and then just Y, but sometimes it's a little bit easier to do both as you go here. So that's what I'm going to do here. So it's a negative 5 and positive 2 for my hk. My dx and my dy are 2 and 3. And I've already determined that since I open up in the x direction, secant goes with the x, but obviously if you're writing that down for the first time there, you got to remember which one is which here. Which one does secant go with and which one does tangent go with. All right, so that's our equation. We're claiming that right there should be the sketch of a hyperbola. This hyperbola we see right there on the screen. Let's see if in fact that is the case. Grab your calculator. And let's go to our y equals menu. And let's put in our equations here. So this time we've got negative 5 plus 2, and it's secant. Secant, remember, is the reciprocal of cosine, so it's divided by the cosine of x, or sorry, of t. And then for y, it was 4 plus 3 times the tangent of t. Now, I'm doing this in degree mode here, so just realize that as I go to set my window here, that I've got to think of this in terms of t values, that I want to go through degrees to sketch this thing. You could do this in radian mode as well, but then you got to use t values that are for radians here. So make sure you got the right mode there that you want to use. So I'm not going to go from negative 10 to 10 anymore. I'm going to go from 0 to 360. I'm going from 0 to 360 because the secant function has a period of 360 degrees. Tangent I only need 180, but secant I need 360. So that's why I'm going to choose that. 0.1 is really small, so probably if you do either 4 or 5 here is going to be decent. I'll go with 5. And I'll sketch this. Well, let's start out in the standard window here, and I might need to move it over to the left a little bit just because of where the center of this was at, but we'll see what we end up with this sketch. Now, that's not too bad. You might move over just a little bit, maybe even up here. Let me do that. Let me change my window here. Let's go from negative 15 to 5. We'll do the same thing in our y direction there. Moving up, we'll go from negative 5 to 15. Yeah, that's not too bad. All right, there's a nice sketch of our hyperbola. And again, if you compare that with the sketch that they gave us, I think we've got a pretty decent sketch of what this hyperbola will look like. All right, look at one more example here. Example 3 on page 511. This time we're going to try to transform from parametric into Cartesian form. So transform the parametric equations to an equivalent Cartesian equation by eliminating the parameter t, thus confirming that the graph is a hyperbola. So this is the same problem we just did. We already know it's supposed to be a hyperbola. The question is, can we get an equation that represents that in Cartesian form? So x is negative 5 plus 2 secant of t, and y is 4 plus 3 tangent of t. All right. The key here is to remember your Pythagorean properties. There's 2 Pythagorean properties that you need to remember. Two Pythagorean properties that you need to remember. The one that we need for this, because it involves secant and tangent, is the fact that, I'll write it this way first. 1 plus tangent squared of t is equal to secant squared. In fact, maybe I'll just write it that way. All right? 1 plus tangent squared is equal to secant squared. That's important because I could solve this for the 1, actually. In fact, I'll go ahead and do that. 1 is equal to secant squared minus tangent squared. And if you notice the equations that I'm given there, those involve secant and tangent. I could solve those for secant and tangent, square them, and then take the difference. And notice that what happens over on the left, the parameter t is gone. It's just equal to 1. That's one that I need to know. And the other one that you need to know is the one involving sine and cosine. Sine squared plus cosine squared is equal to 1. And that's because if you're dealing with an ellipse involves, or a circle, involves sine and cosine. All right, so the same technique we're going to use here can be applied with a circle or an ellipse. All right, so let's take and solve each of these equations here for the trig function. So let's first add the 5 and divide by 2. So I've got, let me put a line here. So I've got x plus 5 divided by 2 is equal to the secant of t. Do the same thing for the other equation. Subtract the 4 and divide by 3. So y minus 4 divided by 3 is the tangent of t. All right, now what I want to do is I want to square both of these equations. So when I square them, I'm going to go ahead and get rid of this one, or at least move this one formula up here. Give me a second, just to get it out of my way, because I want to write right next to this here. All right, so I'm going to take these two equations here. This is kind of my side work there. And I want to square them. So I'm going to end up with x plus 5 over 2 squared is equal to secant squared. You take the other one and square both sides. I'll end up with y minus 4 over 3 squared is equal to tangent squared. And according to what I have up above there, it says that if I take secant squared minus tangent squared, I end up with 1. So let's take these two equations now and subtract them. Take these two equations and subtract. So over on the left, I'll end up with this x plus 5 over 2 squared, and then minus this y minus 4 over 3 squared. And on the right, when I subtract, I end up with secant squared of t minus tangent squared of t. And what we just set up above is what I have over here on the right side is equal to 1. Notice that in that process, I'm getting rid of the t. So I've got x plus 5 over 2 squared minus y minus 4 over 3 squared is equal to 1. If we were to do the same problem again but do it in Cartesian form, this is what we should have come up with. The center is at negative 5, 4. That's our center, negative 5 and 4. Your x dilation is 2 and your y dilation is 3. Our x dilation is 2 and our y dilation is 3. That all checks out there. That is our transformation going from a parametric into Cartesian. All right, that right there is the end of section 10-3.